Okay, excellent. So, welcome everybody to the first talk of 2024. Happy New Year to everybody, and it's fantastic. I very much appreciate David's availability to give us this talk in January. David Rosario is a senior lecturer at Newcastle University in the UK. He did his PhD at the University of Virginia in the United States in 2006, I think it was.
Yeah, 2007, yeah.
And followed by some postdocs at the University of California in Santa Cruz, MPE, Max Planck Institute, and Durham. And his expertise focuses on feedback in galaxies, covering various aspects. I mean, the star formation, AGN interplay, circumstellar regions, etc. David has been involved in a number of large surveys, and most importantly, Candles is one of them. Now there's some James Webb data. And of special interest to our Commission J1 is especially his work, very interesting work on SED fitting with this code FortesFit. We're all intrigued and very interested in hearing you talk about this flexible SED fitting with a Bayesian backbone. So take it away, David. Thank you.
Start sharing. Okay, hopefully you can see that.
Yep. Perfect.
Go straight. Good. Okay, great.
Yep.
All right, well, thank you everyone for joining me. As you can see, I'm sitting in my kitchen. This is the joy of online talks. I have a very busy couple of kids making their noise far away from us. Hopefully they will not come and join the party. So I'm going to talk to you about not research per se, but of course, a lot of work goes into these sort of efforts. And the particular effort I'm going to talk about is FortesFit, which is an SED fitting code, one of many, as you would know, and potentially one that is, you may not have heard of. The main reason being because it serves a certain purpose, and I'm hoping to advertise how it works so that people looking out for that sort of purpose might decide to want to use it. In particular, FortesFit has only a couple of developers right now. I've done a lot of work on it. We only have a few extra people. It'd be really nice to get the community involved because it is available essentially as a community resource. To give some background and maybe some a motivation, let's just look at this image here, right? This is a well-known object, right? M31, the Andromeda Galaxy, seen in X-rays in blue, and infrared emission, thermal infrared emission in orange. These are what galaxies are. They're complicated objects made up of a number of different components, and it's very simple to try to, it's very easy to try to simplify this picture, especially when one wants to look at this object from afar. But in detail, if you look at these objects in detail, there's a lot happening, which is not very easy for us to fold into our general understanding of the objects. In this particular case, the X-rays primarily seem to come from the nucleus, but that isn't AGN emission. It's primarily resolved X-ray binaries. And if you look at the infrared, if you looked at this object from afar, it would be essentially a single blob, maybe barely resolved. But there's a lot of variation in that structure. There's a lot of thermal temperature ranges in this particular object. And understanding this in great detail involves combining information from multiple wavelengths. And that's what SED fitting is, right? We're fitting spectral energy distributions in order to try to get some understanding of this object, modulo the fact that there's a lot of detailed astrophysics underlying it that we might not have a handle on. For example, one might decide that the thermal emission, based on prior information, is tied to something like the star-forming properties of the stellar component in this object. And in fact, there are some quite close relationships between the thermal emission, the dust emission here, and star formation, for example. And the X-ray emission here, for example, might be tied to the old stellar population. In fact, if these are primarily low mass X-ray binaries, there's a close relationship between the amount of old stars and the amount of X-ray emission you get from these binaries. One can understand the system then, not by necessarily looking just at the X-rays and the infrared, but including information that comes from more easily characterizable components, like the stellar component, for example, which could come from spectroscopy, could come from photometry. And we have a long history of understanding stellar components in a population synthesis fashion that can contribute to our understanding of this system. This is where the self-flexibility and the Bayesian approach towards SED fitting comes in, because you can use information from other wavelengths to set priors, essentially, on the various parameters that might describe, say, in this case, the X-ray emission and the infrared emission. Sorry about that. Recovering from a bit of a cold. Anyway, this is what got me to, yeah, there it is. So what got me to FortesFit. This is an effort to try to account for some of the limitations that I was currently dealing with when trying to understand nearby AGN or nearby galaxies in detail. Galaxies which have a vast range of additional ancillary data which would have served as priors for a number of parameters that describe the global emission from the galaxy. So I'm going to describe a little bit of my motivation using a particular example, and then my path towards developing FortesFit. I'm going to talk a bit about the basic elements of FortesFit with some examples as to how you might want to work with it. And then I'll talk about a few current projects that are built upon this code, and then ideas which we are currently putting into practice for future development to make it a more, let's say, a more useful or widely distributable community resource. So let's start with an object, right? A galaxy. This is NGC 5548, very well known. It's iconic because it has been the target of many time domain studies to try to understand the nucleus in great detail. So the central emission from the nucleus is visible in this object, and it has been studied using what's called reverberation mapping, which is a technique to try to figure out the nature of the accretion region, in particular the black hole mass, but also the structure of the broadline region around it, for example. It's a complicated system. There's signs of interactions. There's a big galaxy disk. It's lenticular, so there's some star formation happening, but also very substantial bulge, a number of components that contribute to this source. So let's try to see whether we can understand this source in terms of its SED by doing an SED model. An industry standard, right? One of the most widely used SED modeling codes currently available is SEGAL, for example. SEGAL is particularly good for AGN work because it does include a rather nice set of what's called torus models. So this is dust, AGN heated dust, and also a prescription for the AGN emission in the optical UV. Obviously, this system has stars, and it has dust which is heated by stellar processes. So I'll call that galaxy dust. And this is its SED all the way from the UV to the submillimeter. And here's an attempt to fit it with SEGAL. I'll admit this is probably not the most recent version of SEGAL. The fit was a few years old at this point, but you get the broad idea, right? Now, this looks great. This is actually perfectly good fit if you want to understand this system and get some basic properties, especially as part of a large sample. What would happen if you were to try to include the fact that there's a lot of additional interesting data available for this object? So for example, here is the estimate of the AGN emission only in the UV. This is coming from the reverberation mapping studies I talked about, where you can isolate the emission purely from the AGN at a certain wavelength, in this case, close to Lyman alpha, right? And that's what the measurement is. And here's another measurement. This is a Spitzer spectrum, right? So this is dominated by the AGN, and this is the exact Spitzer spectrum for this object. You can see they don't line up exactly well with the components we expect them to line up with, right? So the AGN emission here is predicted to be much higher from this fit than what's measured. And the SED here has a lot more complexity that we don't really quite capture with this torus model. In particular, for example, these torus models predict very large silicate emission features, which we don't normally see in AGN. So now what do we do now? Is this just because of the limitation of our modeling approach? Or is there something fundamentally wrong? Remember, Segal is a very well-developed SED code. It's perfectly useful for all of these purposes. The reason why it's not quite working perfectly well for this object is because the models are limited. It's not got to do with the technique. It's got to do with the limitation of the model library that was used for this particular purpose. So great. How do we approach this? Well, we just try to integrate more models. This is not a straightforward process. Trying to integrate models of your choice into a standalone code like Segal takes some development effort. It is not something that you would get into immediately. You would talk to Segal people. I worked with the Segal API as well. It's not a very hard job integrating new models, but it is a substantial dev effort, which involves testing, etc. How do we get around that? Well, that's where FortesFit comes in. And the particular aspect where this idea for development came in was when I'm trying to compare, this is a comparative framework, a set of AGN, and in this case, these are SEDs for 20 nearby Seyfert galaxies from the survey called LLAMA, to a set of inactive galaxies, which were matched to the AGN in many ways. And you can see just visually that the AGN, of course, have a lot of extra infrared emission that the galaxies don't have. But there's a substantial amount of diversity in these data. And in particular, in many cases, we have high resolution constraints as well, which allow you to measure subcomponents that are not coming from integrated light. So actually constraints on the components for this galaxy, which give you better information about the makeup of the various components that contribute to this emission. How do we fit these in the best way possible? And how do we, more importantly, come up with a robust comparison between the outputs, the parameters that describe these AGN, and the parameters that describe, sorry, the parameters that describe these galaxies? So in order to do this accurately, first of all, you need to be able to fit multi-component SEDs, take into account the fact that there's a range in parameters that describe the models for each of these objects, the SED models, and then also have a framework which allows you to compare things when you take out, for example, the AGN here, or put very tight constraints on the amount of emission that comes from the AGN, right? So upper limits for some of these parameters had to be taken into account robustly. That's where FortesFit offers both the ability to take diverse sets of models and use a comparative framework, basically a Bayesian framework, to robustly compare these in a statistical fashion. Those are the strengths of the Bayesian approach. So I just briefly told you that real AGN SEDs, which can be seen here in these red and blue models, so these sort of these empirical SEDs, differ quite a bit from model SEDs, because usually the treatment, model SEDs have to assume a simplified description for the AGN environment, whereas real AGN have a lot more complexity. One of the most important sources of complexity is that in model AGN, the dust comes from a very small scale. The dust is confined to a very small scale. In real AGN, they sit in a galaxy, and the AGN can heat dust out to 100 parsecs or more. And so what that does is it produces, in addition to the compact dust right around the nucleus, a bunch of emission, which is cooler and extended. And when you model, for example, this is a set of models that Marco Staleski has put together for a self-consistent treatment of the central emission and the extended AGN dust emission. You can see that you end up producing a lot of relatively cold dust, which has to be taken into account when dealing with AGN, real AGN in real galaxies. How do we approach this? Well, one could try fitting it rather than with these torus models. One could try fitting it with existing empirical SED libraries, like in this case, as I said, these red and blue lines, which come from James Mullaney's work, and Moore and Netzer, for example. And there are a number more which are available now. So in order to deal with all of this, I tried writing my own SED fitting code. And, one might say, like, seriously, is this really something that you want to spend your time doing? I'll be very frank. I did this because I was trying to hedge my bets. In the world of AGN job searches, world of astronomy jobs, it's best to hedge your bets. So I ended up basically writing code in order to learn how to do Bayesian statistical analysis that could then be applied to other things which might be in industry, for example. Thankfully, or not thankfully, depending on which way you think about this, I am still in astronomy, and now I have to teach others how to do this as well, which is a very gratifying job, but it does mean that as a consequence, I have to rely on others to maintain my code because I'm so busy teaching others how to do astronomy. But let me just summarize what I learned from this whole process and how this might be beneficial, for example, for your particular applications, right? So I found that most astronomical SED models can be described as a single parameter that sets the scale of the model. And this could be a simple, a basic parameter, or it could be something rather more complex. But typically you can cut this down to a single, what's called a scale parameter, and then a number of parameters that change the shape of those SEDs. So I would distinguish them from shape parameters and scale parameters. And just to give you an example, this is a type of model that many of you are probably familiar with. These are stellar population synthesis models, right? Describing galaxies. In particular, we're using the Bourgeois and Charlot 03 model library here. And these are solar metallicity models with using sort of tau model descriptions for the star formation history. And I'm just plotting here a set of SEDs at a fixed tau, for example, a fixed exponential time scale, but with different ages, right? So you have a young age for this sort of recently formed galaxy, which has an exponentially decreasing star formation. The galaxy formed 3 million years ago, so this would be applicable for galaxies at higher redshift, or galaxy formed 11 billion years ago, in which case it would be similar to a galaxy we might find today. The only thing that connects all of this is a fixed stellar mass. And what you're seeing here is, as the stellar mass increases, as the age increases, the light from the galaxy drops, but the mass remains the same. And we all familiar with this. The mass to light ratio is changing with age. This is a well understood effect. In this case, I wouldn't, for example, use light at a given wavelength to be a scale parameter. I would choose stellar mass to be a scale parameter, and vary the ages and the taus and the metallicities, for example, to describe a range of SEDs that then encapsulate a model to explain this galaxy, right? And in this case, the single scale parameter is stellar mass. And one can do this for many different models, some more complex than others, but essentially you can summarize models as a combination of a scale parameter and a range of shape parameters. If you cannot, you can take your model and break it up into two components that you can then add together and then play that game, right? That would be the approach. The other thing I found, especially dealing with nearby galaxies, and often with high redshift AGN as well, is there's a range of ancillary data. And this is especially the case in our era of surveys, right? Multi-wavelength surveys is where we concentrate a lot of our effort now. And that effort allows us to take advantage of the ancillary data available from many different bands, giving us a range of potential priors. What is a prior in my mind? This is a way to constrain the probability distribution of a parameter that describes an SED. So in this case, what is the probability distribution on the age of these galaxies, right? Well, a simple thing would be that if you're forming a galaxy 1 gigayear after the Big Bang, well, the minimum age, the maximum age of this galaxy has to be a gigayear, right? That's a simple prior on the age of the object, and that would be an example of a physical prior. You might, for example, say that based on its K-band luminosity, which may come from your survey, it cannot have a mass that's more than 10 to the 10 solar masses, and that's a prior on the stellar mass of the system. These are various priors that one might be able to apply in a probabilistic fashion, of course, because the K-band luminosity is not one-to-one related to stellar mass. There's a range of potential stellar masses tied to a K-band luminosity measurement, which has its own uncertainty, and therefore probabilistically you can put a constraint on the stellar mass range and distribution, but you don't want it tied to a single value. And then let me just go back to 5548, because this is the example of an object with just an enormous range of prior information. We know its black hole mass, we know its accretion disk luminosity, independent of variations which come from continuum variations, for example. We know what it's doing in the infrared because of spectroscopy that's currently available. It's a huge amount of data for this particular object, and we want to be able to fold that data into our SED fit to get the most realistic description of the parameters that describe the galaxy as a whole. And finally, a question of style. I find that if you were to plot an SED and then compare it to a set of models, and you do it in your typical F nu space or F lambda space, where essentially you're looking at some sort of intensity, intensity per unit wavelength or frequency. That galaxies often show a broad range in those numbers. So you're looking at plots that cover a very large dynamic range on the y-axis, for example, and I'll show you an example of this. That tends to hide disagreements between models and data. So I always plot my plots in nu F nu, because galaxies tend to have relatively flat SED in these units, and that brings out disagreements, which is what we want to do when we're trying to fit SEDs. Right. So what is FortesFit and why is it useful? So it's a Python 3 package. It's not a complicated thing. It's written in Python 3 primarily because it's supposed to offer, well, let's put it this way. The actual fitting, the detailed fitting is usually done by third-party codes like MC or multinestic, for example, which are based on C, for example, right? So Python FortesFit is primarily a way to take the data you provide, put it into a format that can be then given to a fitting engine, which then does most of the hard work. That's perfectly good for Python, because Python is widely used in the community, and it offers a lot of nice resources for interaction with data. Whereas if I were to try to write, the actual SED, the likelihood, Bayesian likelihood analysis and optimization using Python, that would be a terrible idea. There are better codes to do that, and FortesFit intersects with those codes in order to do what it does. It requires some basic libraries which are easily available. You can get it on GitHub if you want. I would request anyone who's potentially thinking of downloading it right now to wait just a little bit, because the GitHub version is fine, but it's also available through pip. And there have been recent changes in the way that some of these Python codes like NumPy, for example, have made some changes in the way they interact with, for example, even basic things like data format changing and stuff like that. So they're trying to fix this for a moment. If you decide you want to use it immediately, just let me know first, before you try to install it, okay? But co-developers are very welcome. Now, as I said, FortesFit is fundamentally Bayesian. This is not Bayes' formula. This is a tongue-in-cheek modification for Bayes' theorem from the comic strip XKCD, which tells you that how well you use Bayes' theorem depends on how well you understand Bayesian statistics, right? And sure enough, Bayesian statistics is not necessarily a straightforward thing to get your head around. You know, it is a fundamentally different approach towards how we deal with data. But for SED fitting, it makes complete sense, right? Because we are trying to constrain the parameters of a population, of a model that describes our limited data by taking into account what we know about the system from other independent ways, that is through priors. So the key elements in FortesFit are this thing called the model. The model is something that you register. This is something where the user works with the code to register a model that is provide the code with a function that takes in, for example, redshifts, model parameters, and a set of, say, photometric filters, and spits out an SED and spits out a set of yeah, exactly. So it spits out an SED that the model code can then use to generate model photometry. So the model code generates model photometry. The user's main aim is to allow the code to understand the model that it's using, which means that if you supply some parameters and let's say a redshift, you get an SED that describes the full range, say UV to infrared, up to the user to decide. And you vary the parameters of this model and you get different SEDs. So a function that does that, sort of a function that's understood by the user, is provided to FortesFit with a certain format. FortesFit runs through all the possible range of parameters, all the possible range in redshifts that you might need for your application, all the possible filters that it has in its library, for example, and generates model photometry in a format that can then be used for SED fitting. Now, this is where the flexibility comes in, because you, as a user, decide what models to use. I can provide you with some set of models, which I have registered before. That's perfectly suitable for if you're sharing applications. But you might decide that David's set of models are limited in scope. And I have a new set of models from my good collaborator here who understands these things in more detail. I want to try to include them in my fits. Or you register the models yourself and use them. And the registration itself is a one-time thing. Doesn't take an exceeding amount of time. We use multiprocessing currently to speed up the process of registering. If it's a huge model library with, say, 16 parameters or something like that, it could take a little while. But most models don't have that large range of parameters. For example, the BCO3 model that I have there has about 3 or 4 parameters, I believe, and the registration takes about an hour for the full SED model library. And then I can use it for any number of fits. You can combine models into a fit, like you can combine an AGN and a galaxy and other dust components. And this is something which I'm particularly happy about. This is the concept of a dependency. So you might describe your models using a set of parameters. Let's consider the BCO3 model we looked at earlier, the stellar population synthesis model. In the model itself has stellar mass, age, exponential time scale, metallicity, and maybe dust extinction as some set, like 5 parameters. But in terms of a measurable constraint on those models, you often don't have any of them, really. We might have something like a K-band luminosity, right? A K-band flux even. Or you might have a star formation rate estimated from the far infrared or something like that, or from spectroscopy, something that isn't a parameter that the model is described upon, but is related to those parameters. And that way, what you can do is you can define dependencies tied to a model. And an example could be the star formation rate. For each model, there is a star formation rate estimate. That star formation rate estimate is treated as a dependency and defined when you register the model. It can be done after the fact as well. And when you do your SED fitting, you use the dependency to do the SED fit rather than the constraint on the model parameters themselves, right? How do you do those? How do you do that? You use a prior. Now, FortesFit requires a prior on every parameter in the fit. If you don't supply a prior, it's assumed to be uninformative. So it essentially just covers uniformly, gives probability to all the possible range of parameter values that were used during registration. Some parameters require a prior. Scale parameters, the single scale parameter for every model requires a prior. It can be as big or as small as you want, but you need to provide some constraint on the stellar mass before you can do a fit. In this case, for BCO3, for example. But you can also put priors on the dependencies. So I might decide that I can put a prior on the star formation rate for a galaxy based on its far infrared luminosity. If I have defined the star formation rate to be a dependency, then I can use FortesFit to constrain my SED, constrain my stellar population using the star formation rate as an example, using the star formation rate as a constraint, even though it's not technically a parameter for the model. And prior specification can be very flexible. So you can use any SciPy stats distribution as long as it's continuous currently. You can even use your own 1D grid. So for example, if you want to use a photometric redshift prior, often that comes out of some third-party photometric redshift fitting code. That could be just in the form of a XY grid, right? Just a histogram. You can use that as a prior, for example, in this fit. And there is the capability to handle photometric redshifts in the form of priors. I will freely admit that this is a complicated thing to do correctly. And FortesFit should not be treated as a photometric redshift SED fitting code, photometric redshift code. There are better codes to do that. But if you do have a large range in photometric redshift on a particular source, you could fold that in to your fit, and then the posteriors that come out of this whole analysis will reflect your uncertainty on the redshift. The SED fitting is done using Markov chain type codes. MC is built in, but I tend to use multi-nest, which I find nested sampling to be a very effective tool for this sort of work. Multi-component, relatively large parameter space SED fitting. Nested sampling is a very powerful, very powerful algorithm for this. And FortesFit includes some capability to link to multi-nest with very minimal additional. You have to basically set up multi-nest on your machine, which is a third-party application. So that needs to be done first. And once you do that, then everything else should work. Currently, likelihoods assumed to be Gaussian. If, for example, you might want a different set of likelihoods, you might, this could be something we develop. But almost in all SED fitting cases, from the UV to the submillimeter, you can generally adopt chi-square likelihoods, so Gaussian combinations of Gaussian likelihoods. And then you have access to a number of different nice output components. You can get the chains directly, which are stored. You also have high-level access to summary statistics, relative entropy to look at how much you improve your fit over what you've initially provided. So the information gained from the fit, which something comes out of Bayesian analysis. We also store things like the Bayesian evidence, which allows you to compare different model fits. This is a little tricky to interpret, but the Bayesian evidence is stored. You can visualize convergence, you can visualize marginalized posteriors, model SED. So let me just show you an example of this, right? Let's get back to NGC 5548. This is what I've shown you before. How can we improve on this? So let's start first of all with the AGN, because that's what I work on. I told you a little bit about how there are different empirical models for an AGN. One really useful model is this so-called decompIR model library, which James Mullaney developed and published in 2011. And it's quite simple. It's treating the AGN SED as a combination of power laws with some drop-offs, some physically motivated drop-offs. So a coal dust drop-off, a dust sublimation drop-off, and then a couple of power laws with a turnover in the infrared. This apparently works really well for AGN studied with Spitzer in gory detail in the local universe. So we included it as a model for the AGN emission. We included priors on the AGN emission in a very simple way. For example, in this case, there's a well-known relationship between, say, the 12-micron luminosity of an AGN and the X-ray luminosity. And for all of our AGN, we have independent X-ray luminosity estimates. So we can take this relationship, including the scatter in this relationship as a statistical variation on this prior. So if I take the X-ray luminosity, that means that I know the infrared luminosity within some range, or within some range, and then I can tie that infrared luminosity to my model, and that sets, for example, the scale parameter, and then the shape parameters can be varied over the full possible range that's available for this model. So that's the infrared component. There's an optical component for the AGN. One might say that the optical should be tied to the infrared. Maybe, maybe not. We are unsure. I just treated them as independent components because they are coming from different parts of an AGN. So this comes from the accretion disk. There are models for the accretion disk emission for AGN. This is a simple one-dimensional model coming from Sloan and Netzer. And this range of SEDs here capture the expected variation in the in this accretion disk emission as a function of black hole mass and AGN accretion rate, for example. So that that's something that I incorporated into the simple model. Now, can I use this? Can I use a prior for this as well? Yes, indeed. Some people have studied, for example, the relationship between X-ray luminosity, and this is missing a y-axis label. This should be X-ray luminosity at 2 microns, and then the 2500 angstrom UV luminosity. So the UV luminosity is something that we can constrain, say at 2500 angstroms there. And the X-ray luminosity is an independent measurement coming from X-ray surveys. And there's this relationship here between the two, which has been validated on large samples of quasars by, for example, Lusso et al. I can treat that as a prior, and because I know the scatter, I can take that as a probabilistic prior on the UV luminosity, right? These are both tied to the X-rays, but they're both somewhat independent estimates. The infrared luminosity and the X-ray luminosity are independently the UV luminosity and the infrared luminosity are independently tied to the X-rays using independent descriptions of the prior. And for this particular object, NGC 5548, I worked with this setup. I used the BCO3 model as well. I have 13 parameters, including dust, that I used to fit this object. Here's a classic corner plot. If you're not familiar with this, this just shows you both the distribution of all these parameters after the fit. So that's called a posterior distribution. And then also how the two combinations of parameters correlate with each other, right? So this deals with covariance between parameters. In this case, for example, I can't tell you which these two are. These two are related to each other. And Bayesian techniques allow you to marginalize over these relationships before giving you posteriors. This parameter fit, 13 parameters, 400 live points. Took me 30 minutes on a single core on my laptop. So it's a particularly well-written code, in my opinion. It's relatively fast for these applications. So how does the fit look? This is 5548 after the fit. This is the AGN accretion disk. This is the stars. This is the AGN dust emission, and this is the galaxy dust, right? You can see it's actually remarkably good. I didn't expect it to be so good. We're getting the UV luminosity as derived from reverberation mapping constraints, we're getting pretty much exactly the shape of the Spitzer spectrum. And remember, the Spitzer spectrum and this UV luminosity were not used in the fit. So independent checks of the output. As a consequence of all of this, we also get things like, the extinction in the towards the accretion disk, the extinction in the stellar component in an average fashion, various shape parameters for both the AGN torus and the galaxy infrared component here, which is treated as a single component model. It's a simplified model, but it works remarkably well for this object. And because I have this model, I can now apply it to all of the objects from that initial survey that I talked to you about. And that's I wouldn't say that's work in progress at some level. So I don't have any results for that yet. But the approach is similar, right? We can use FortesFit with a consistent model now for 40 objects without any issues. And what you get out of this is constraints on many different parameters, and not just a single point estimate with some uncertainty. You get a full distribution of the output. These posterior distributions marginalized over the range in possibilities shown by other parameters. So this is a realistic description of your uncertainty, not a point estimate that may come from, say, a least squares fitting. When you have a rather complicated likelihood space, you want to be able to marginalize over the posteriors of these the full posterior distribution as accurately as possible. So in this case, I can constrain most of the luminosities quite well. The stellar mass, for example, infrared luminosity. I can constrain things like the extinction reasonably well for the galaxy, maybe not so well for the AGN. I can constrain some parameters of the AGN torus, but many of them I can't. This is not a good constraint. However, I can constrain the galaxy dust emission quite well. Let's see, we got not much time. So what I'm going to talk about now is just a couple of different applications in the literature, just to give you a sample of how people have been using this code for various applications. I will concentrate primarily on AGN work because that's what it's mostly been involved in. So people who want to apply this to galaxy science, you may have other codes that work equally well, but FortesFit is the only one that can include a range of other components. If you are careful about the AGN, or you are worried about a more complex model which is not being captured by other codes. It can also be used for galactic science or stellar science. There's no reason why it has to be extragalactic work. The main reason being because we're agnostic to what models you use, right? All you need to do is describe distribution of light here. You can use them as long as you can cast a model into a form which has a single scale parameter and a range of shape parameters. You can describe any SED, and as long as you can do that, you can use FortesFit, right? So don't think of it purely as an extragalactic tool. Here's a very nice study that came out a couple of years ago. This is Carolina Andoni's study based in Durham. What she led doing was to take FortesFit, the strength of FortesFit, which allows you to take complicated models and then put probabilistic constraints on the priors to simplify the models at some level, rather than just take point estimates for the parameters. She selected a large number of AGN, or by studying about 3,000 sources, a large number of AGN in the Cosmos survey. And we defended the case that it's a complete selection of quasars in Cosmos. That is, it finds powerful AGN, quasars, even if they were heavily obscured. So you wouldn't see the optical emission. You could only detect them by looking at the entire SED. And from that sample, here's just an example. For example, this is a couple of SEDs fit with FortesFit. And in this case, you can see a stellar component in yellow, a AGN torus component in red, and a galaxy dust component here in blue. And in the unobscured systems, you also have some emission coming from the accretion disk, which is in green. So here's an obscured AGN, which shows strong AGN emission in the infrared, nothing in the optical UV. And here's a similarly luminous unobscured AGN, where you start to see the UV emission. And because we have the full correlation between the various parameters, we can robustly identify unobscured and unobscured systems using X-rays and SED fits. And what I particularly like this plot here, what Carolina did here was to show all the best fit SEDs for all of the sources. That's these gray lines. And then also split them into obscured solid lines and unobscured dashed lines. And you can see these differences between the median SEDs of obscured and unobscured AGN. And we can explain this not as a single SED, but as the differences in various subcomponents. So for example, unobscured AGN have a stronger, as expected, a stronger UV, a stronger accretion disk component, but also we find differences in the stellar component. And I think what really jumps out is differences in the galaxy dust component. The star formation heated dust is much more powerful by a factor of 3 in the obscured AGN compared to the unobscured AGN. We can test this robustly using FortesFit. And this is, in my opinion, some of the best evidence that obscured quasars, so these are the AGN responsible for primary black hole growth at redshifts greater than 1. These systems have differences in their star formation rates at quite a substantial level. So the obscured quasars, the ones that are harder to find, turn out to be primarily in starbursting systems. So this is this evolutionary connection between the growth of black holes and the growth of galaxies we can find in a statistical fashion by using FortesFit to probabilistically tease apart the differences from this population, both the selection and the scientific result. I think I know we're running out of time, so I'm not going to spend too much time on the rest. We have applied it to a subset of high redshift AGN, which have kinematic information. So this is the CASH-Z survey or CASH-Z survey. And the main aim of this was to pull out these parameters, but we also did a comparison between SIGAL and FortesFit, and everything looks really good. So FortesFit's model, the model that I just described for the AGN, is completely consistent with what the industry standard like SIGAL is using. And in particular, the galaxy dust luminosity, so this is the star formation rate, and the stellar mass are 1-to-1. The scatters are very consistent with each other. I'll highlight here a couple of tests of the system of the code and the modeling parameters for the AGN. This is a comparison of what I get for nearby AGN, what I get at 12 microns from my SED fits, to direct measurements of 12 micron luminosities from 8 to 10 meter mid-infrared instruments on the ground. And it's remarkably clean. I mean, it's, the SED fitting here, which uses X-ray luminosity as a prior, somehow ends up getting the AGN luminosity to better than the accuracy of the prior, right? So this is just telling you that AGN are behaving in an understandable fashion in the mid-infrared. And this is work in progress, and I don't quite have a full set of plots for this, but my student here at Newcastle is using the power of JWST. In particular, what Webb is allowing us to do is zoom in on the nuclear emission from galaxies at redshifts greater than 1 and take out, because it's resolved in the mid-infrared, actually take out the galaxy emission. So zoom in on the nuclear AGN emission, separate the nuclear emission from the extended emission. And here's an example of JWST imaging for a galaxy in the Sears survey. And we can really pull apart the emission from the central roughly kiloparsec compared to the entire galaxy. Here's a comparison of what we see. For example, this is a ratio of the luminosity at 1.6 microns rest compared between the integrated light and the JWST nuclear light. You can see that we can separate out, we can basically get rid of, sometimes as much as 15 times the nuclear light can be removed by looking at these very small apertures. And that allows us to model the AGN in a fashion that has never been able to do before. So we can identify AGN emission in galaxies where the AGN is too faint to have been picked out by basically zooming on the central nuclear emission. And this is working quite well. And the advantage of FortesFit here is that we can use a rather complicated model that includes both resolved emission and unresolved emission in the same model. So we can apply the same priors to both. We can apply the same constraints and use the same data sets, both resolved and unresolved, to put sharper, better constraints on the AGN emission than before. So I'll end there with a quick summary. FortesFit is, I think, particularly powerful. There's a little bit of work needed to get to use it, because registering a model is something that requires the user to understand the models very effectively, so that they can correctly integrate them into FortesFit. If they make errors in registering the model, the fit is going to be wrong. Okay, so some work is needed in actually coding up a model. However, we do have currently developing a way to share models, basically share the registration code and the background data for a model, so that a user can register a model without having to write the registration code themselves, if you see what I mean, write the registration function themselves. We can take into account rather flexible set of priors. And this is exactly what I said. We're trying to use this AGN model as a prototype for a community-driven way to describe models. So people can do the hard work of registering models, coming up with the registration scripts, and then provide them to the community, for the community to download, register models, and use them using the Bayesian background of FortesFit. So I'll stop there and happily take any questions.
Okay, so thanks, David. Great talk. I really enjoyed it. It's really fascinating stuff. And so I imagine that people will have questions. Please raise your hand. Let's see if I can see you here. So unfortunately, those that will be joining us through YouTube will not have that chance.
Yes, indeed.
So, I mean, I have a number of questions. I mean, definitely, the first one is definitely, you're putting together many different things in fitting. You have SED fitting of different components that can vary in different ways. So the first question is at the more fundamental level, degeneracy. So for instance, I'm just thinking out loud, if you're fitting the region between ultraviolet and optical, you have most of the contribution coming from either the accretion disk and the stellar populations. So one question I may have is, if for any reason, can you actually interplay these two, so that if you change the accretion disk, suddenly the stellar populations are different? How can you beat that type of degeneracy?
Yes, absolutely. That's the crucial driver between this. Realistic, I'll just go back maybe to those AGN accretion disk models, right? Without a constraint on the scale for this looks remarkably like a galaxy. Or, let's put it another way, a galaxy can look remarkably like an obscured AGN. Not the blue models don't look like galaxies because they're too blue, but the obscured models like these, or these sort of high mass, these are high mass black hole models, they kind of look like galaxies at some level. And so there is a huge degeneracy if you're not careful, if you take a full range of AGN models and try to fit them with population synthesis galaxy models, especially if you include dust. So FortesFit allows you because it's Bayesian, because you're covering the full parameter range, to determine where these degeneracies lie. So these corner plots, for example, show you the parameters that are degenerate. Here we go. So this is degeneracy. This is where two parameters play off each other, right? In this case, for example, we're comparing 1 and 2. The luminosity and the extinction are basically playing off each other.
Yep.
Now, we can't remove that degeneracy. We can deal with its effects, and therefore its effects on the uncertainties of the final fit and the parameters, by doing it in this fashion. But if one wants to make a constraint, one can apply a prior. So in this particular case, I do have a good constraint on the luminosity from the accretion disk, and that constraint came from the X-rays. I might decide, rather than doing it from the X-rays, I might treat this as a direct measurement of the AGN luminosity in the UV. This is indeed is a direct measurement of the AGN luminosity in UV. I could have taken this as my prior, and that would restrict the blue light to lie within this range. Now, that helps to break some of this degeneracy. If I had more constraints from additional approaches, so if, for example, if someone took the spectrum of this object, right, and could separate out the light coming from the AGN and the light coming from the stars in the optical, and then basically restrict the AGN light to lie in that regime, that would be an additional prior constraint that one could apply. And FortesFit allows you to fold those priors in by carefully registering models in the right way. So that, that's how one breaks these degeneracies, by using ancillary data. Otherwise, with the absence of that, FortesFit at least shows you, or any Bayesian code, not just FortesFit, any Bayesian code will show you the true amount of those degeneracies, right? In many codes, the approach taken to break degeneracies is to tie parameters to a single value. So you might say, well, I can break this degeneracy by reducing the number of parameters, right? That's fine. That is perfectly sensible, but that is a very strong prior. You're basically saying that in the real universe that I'm looking at, galaxies only have one value for this particular parameter that describes the SED. That's not the way the galaxies work, right? Galaxies have a broad range in all parameters, especially if there's a physical reason for a variation in that parameter. So a Bayesian code will agree that there's a variation and take it into account. That does mean larger uncertainties in your output, but at least you have those uncertainties under control. That's your real information about the universe, if you see what I mean.
Yeah. No, that's a good point. I could imagine another one that you might be using is, for instance, something like the energy balance. So you're basically getting the emission in the far infrared, and then you try to say, well, this is coming both from whatever dust is being attenuated in stars and in the AGN. So in this work, I mean, this is work in preparation, I imagine, so I'm looking forward to this James Webb data. So as you're actually going towards smaller apertures, I can imagine that some level of estimates of the color gradients or variations in the colors will very clearly inform you of this trade-off, for instance, between the accretion disk and the stellar populations. Have you been doing some work on this so far? Can you say anything, or is it?
We have looked at colors. Yeah. So yes. So yes. So broadly, there is, and I wish I could show you this. Actually, I don't have a good figure to show this yet. The central region shows often very different SEDs from the extended region. And the central region very often shows SEDs that one could interpret better with a smooth AGN rather than a galaxy SED which shows breaks. So what this is telling us is, now I'll be very frank, we are looking, for this first paper, we are looking at known AGN, right? We're looking at X-ray sources. So we are selecting things which have AGN in them. There is an approach for trying to do this in samples where we don't know there's an AGN. So essentially looking at all JWST selected galaxies and look for AGN in their central regions. It's harder work than one would take to be, because of the range in PSFs, essentially, in the point spread function across these bands. It has to be done carefully. But we have that in mind. As a proof of concept, we're just looking at known AGN and try to see whether we can constrain the parameters that describe the torus, these parameters, in a better way than if we did it with just integrated photometry, by allowing us to basically pull out this emission, essentially, this emission using JWST for the first time.
Okay, looks good. Okay, so just one final thing. I have many questions, but I don't want to bore you with with this. We will have the chance to talk at some later time. But I'm just wondering, on top of the standard SED fitting, are you considering, for instance, the possibility of using the emission lines? So using them as additional type of information, at least let's say in the optical, the typical BPT type of diagnostics.
Yeah. There is. Oh, let's put it this way. There's two elements. There's using emission lines as priors. So using emission lines to come up with priors for the other properties, other parameters. Let's say, O3 luminosity could be a prior on the AGN luminosity, something like that, right? Or actually looking at ways that the emission lines affect the photometry. Right? There's contaminants and there's information. Using information from emission lines, we absolutely do it already. So, for example, I use information from emission lines to constrain AGN luminosities for the nearby AGN, right? For example, currently we are thinking of the best way to deal with contaminants, right? How do you contaminate? How do you correct for line emission in each of these photometric bands? This is a bit tricky because it is dependent. It's cross-dependent on the properties of the galaxy, right? So there's a little bit of sort of a circular argument there. In most cases, it makes almost no difference to the overall fit because the emission lines don't affect the photometry too much. But there are specialized cases where it might, and so we're thinking of the best way to deal with emission line as contaminants to photometry in the best way possible, maybe as an additional parameter that you can marginalize over. But currently, we can absolutely take emission line information as priors.
Right. Well, excellent. I think that was very nice. Thanks so much, David, for your talk. Looking forward to your papers on James Webb applications, and we will be in touch actually with this FortesFit. I'm very, very interested on that. So,
absolutely, yes. Please, anyone interested, feel free to contact me. If you want to try using it, let me know. I will try my best now that I have students working with me on this as well to try to give you the support that you need.
Excellent. So if you don't mind, what I can do is actually once I post this video on YouTube, I can put in the description, you can say people interested in using FortesFit can contact David at this, and then I put your email address. I think that would be a possibility. All right, great. Okay, thanks so much, David. Thank you for taking this. Giving the volunteering for giving this first year New Year's talk. So
pleasure.
Thanks so much.
My pleasure. Good to talk to everyone. All the best.
Take care. Bye.